Log on, tune in, find out. Another good idea from Cambridge.
Is Balazs Szendroi, who will speak on Motivic Donaldson-Thomas theory of the conifolds.
Okay, thank you. I hope you guys are all very interested in Motivic DT because, So my plan with the chairman's permission is to talk for the whole afternoon, and whoever has a train at a certain time can start leaving, right? Okay, so before I start, let me just mention, so this is a project with, so I can't really seem to be able to do anything these days alone, so I've got some collaborators here, collaborators. So so this is now a joint project, so the list is growing, so Andrew Morrison, who was mentioned earlier, Sergei Mozgovoi, we've now recruited, and Kentaro Nagao. And also very close related results by my student Ben Davison, although quite who will end up writing the final paper, we'll see when we get there. If you're interested in joining the team, let me know. We are just advertising some, there's some openings, so we can talk about it. Right. So, and I've also decided to. This is the last talk, so I'll be taking a slightly historical approach. So I want to tell you everything about the conifold. This will involve things like, when Rahul was young and that kind of stuff. So, okay. So introduction. So we're talking about the geometry, which is the local P1. So it's the simplest geometry beyond C3. It's the simplest Calabi-Yau geometry, which at least has a curve in it. So it's got the zero section, one proper curve, and it's been very fruitful to study this example. So I hope by the end I'll convince you that it's rich enough to deserve still the kind of ongoing attention. So what do we know about it? So we know that there is a flop birational map which takes out the zero section and glues it back again slightly differently. Of course, happens to be isomorphic for this local example, but this is still a non-trivial transformation. And then related to this geometry, there is the algebra. So this is a non-commutative C algebra, which is J. So implicitly been mentioned for related examples. So this is the path algebra of a quiver divided by some relations which are given by partials of a superpotential. So here, for the particular example, Q's got two arrows going that way and two going that way for two vertices. And then there's a superpotential, which is the so-called Klebanov-Witten ACVD minus ADBC, Klebanov-Witten superpotential. So there's a related quiver and the related algebra. So
what do the double brackets mean?
Two-sided ideal generated by.
There's no completion going on.
No, there's no completion. No, sorry. That's just, yeah. So there's a related algebra. So I'm going to clash with Jim's notation. You should have called your reduced quiver Q bar. I'm sorry. Q tilde is the extended quiver. So my Q tilde is, if I change notation now, I'm going to make a mistake all the time. So Q tilde is the extended quiver or framed quiver. So there's correspondingly a J tilde, which is CQ tilde. And actually, we haven't introduced any new new loops. So it's the same superpotential. It doesn't make sense to put anything else. Of course, the story changes completely if I allow an arrow backwards, but I don't. So this is a simple story and a rank 1 story. So this will always have either dimension vector 1, so it will be there with a one-dimensional framing, or it won't be there at all, in which case we are back to where we started from. And so just because Richard insisted, I should put in something about derived categories. So there's this well-known theorem in this formulation due to Bondan and Orlov. Part of it, Tom generalized it, of course, and the algebra side was studied by Michel van den Berg, which states that the derived category of coherent sheaves on X is equivalent to the derived category of finitely generated modules for Jacobi algebra, and it's equivalent to also to the derived category of coherent sheaves on the flow. So if you want, this is some sort of autoequivalence if you then want to interpret X plus is isomorphic to X. But there are really three kind of players there. Okay, so this is all the objects. Okay, so the objects you're studying sort of can be thought of as living in these derived categories, although, of course, when you bring in the framing, then they interpret it slightly differently. So let me talk about some enumerative theories here. So this is going to be the sort of classical story. I'll be enumerative. Okay, counting. Counting theories. You know what I mean. So there is, of course, the kind of classical dt invariant. So this is the dt invariant of X. So d and n. So this is, as introduced by MNOP, this is the counting invariant of rank 1 ideal sheaves. Ideal sheaves of certain topological type. So here my D is going to be a class in sort of H lower 2, which is just one-dimensional, and then N is the degree class, so of type D and N. So these are really just thickened ideals of the zero section, the curve part, and then the point part can wander about arbitrarily. So this is the virtual number of these guys. So which is, you could interpret this either after localization or as the value of the integral of the Barrand function in this, on these singular moduli spaces. And then if you put them in a generating series, so this is now very well known. So this is some dt x dn, and then t to the d, y to the n. So that's your dt partition, rank 1 dt partition function, summed over all d and n. And so this can be computed via torus localization. And if you do that, so the reason is that this is a toric variety, so there's a big torus section. You might want to only take the part of the torus section which is a Calabi-Yau torus, so there's some technical details. But if you do that, then your computation is going to reduce to this thing called a toric web, which is basically a picture of the torus invariant lines and points and lines in this geometry. So this central line is referring to the compact P1 direction, and then there are some non-compact directions on either side. So what is, when you compute, then you have to think about what are the torus fixed points on these ideal sheaves. So this is all very standard, and you get to these combinatorial configurations, which I'm going to sketch very schematically. So the sort of combinatorics, so there's some flat part here. So this is meant to be a kind of very schematic picture of what a torus fixed point looks like. So what is this? So there's some kind of flat part in this picture, which is some kind of partition, two-dimensional partition, and if I'm computing a particular invariant here, that's meant to be a partition of D. And what's this part and that part are these 3D or planar partitions, 3D partition. So you're led to some kind of combinatorial problem where you're counting planar partitions or 3D partitions which have a kind of asymptotic behavior along one of the legs. And that is asymptotics is given by this partition lambda, and now you're supposed to glue two of them together. So how does that give you a computation of this? So this gives you a computation because, I mean, after some work, so this is work of Malik et al., you reduce this to kind of sum over all lambda, and now there are these expressions which I'm going to use the full notation just for the fun of it. So these C's, they are called a topological vertex, and these are these combinatorial sums, the generating series of these combinatorial configurations. And so for some reason, there's some framing issue, there's some orientation issue. So here the empty refers to the fact that there are no partitions, no asymptotics on these sides. These are non-compact directions, so the combinatorics is not allowed to go out to infinity, but in this direction it is. And there's this profile lambda. So as it happens, if you glue it backwards, then you have to take the transpose partition, and then the t variable is going to come just in this simple form. So this thing here is called the topological vertex, or I mean, one usually normalizes by the McMahon, but I don't want to spend time on that. So in general, this combinatorial expression is called the topological vertex, and it's been studied in lots of papers. But I mean, certainly Andrei Okonkov played a big role. So Okonkov, Reshetikin, maybe Waffa, MNOP, and lots of people. And originally it was discovered in physics by Danagic, Clem, Marino, and Waffa. Okay.
There's not some gluing factor?
Kind of subsuming the glue. I mean, you know the details better than I do. Can I just sort of stay on this level of, I mean, you know, you can, yeah, I've incorporated the gluing factors. But this is actually a computation because this turns out to be just a Schur polynomial. So this particular simple one turns out to be a Schur polynomial. So you get a factor of McMahon squared from from each of these that sort of factors out, and then the answer turns out to be some kind of Schur polynomial, S lambda evaluated at minus q to the rho. Let me just not explain in any great detail what these things are, but there is some kind of very explicit computation, t to the lambda. So the point is that you get an infinite product in the end. So at this point, there is some kind of Schur function identity, which turns this into a very explicit infinite product. Product m greater or equal to 1 minus y to the m t to the m. Okay, so that's the answer. So here is a full dt series computed via localization. And so this is a kind of famous function. There's many expansions of this. So you can use this to check the MNOP conjecture, connect it to Gromov-Witten theory, connect it to 1 over d cubed, connect it to these computations of Faber and Pandey-Pandey, and so on. This kind of incorporates a lot of the simple stories. So multiple covers of a single P1, normal bundle -1, -1. So that's all, in some sense, starting here. Okay, so there's a kind of different enumerative story that you can tell here. So you can also approach. So there's a kind of counting of framed modules, so J-tilde modules. So now you kind of look at that derived equivalence and say, okay, we've done something on this side. How about thinking of that side? So when you do that, then what's the first thing you might count? I mean, somehow classically that was the natural thing to do, was to count. So there's some kind of dt invariant associated to this J-tilde, and it's got two. Now that the K-theory is sort of described by two integers, or positive integers in this case. So these are just the dimensions. So dimensions of the rep. So I've got dimension 1 here in this case. I'm talking about j hat, and then n1 and n2, and plus the cyclicity condition. So the cyclicity condition says that the image of this arrow generates the whole representation. So that's the stability condition, and if you do that, then you get to a very pleasant moduli problem where stable equals semi-stable, and everything works out very nicely. So you get a numerical invariant, and you can also turn that into a generating series, so some kind of zj tilde of y0 and y1, which is just the generating series. And we write it down. And so that can also be computed. So there is another, so I want to keep that. So this is the zx yt. Let me keep that. And then the point is that there is the torus action still applies here, and you get a different combinatorics. You get what's called a crystal combinatorics, a different crystal, I should say. So let me again not give you all the details, but this Z J tilde y0, y1 can also be computed by torus localization, where now the torus invariant clusters, the torus invariant J hat modules are going to be some kind of, you kind of got to take the universal cover in some sense of this quiver that gives you a kind of infinite pyramid configuration, and you have to take certain finite subsets thereof. So there's some kind of combinatorics that you understand very well, and that leads to a kind of theorem which I conjectured and then was proven first by Ben Young. Now there are several proofs, which says that this Zj tilde at y0, y1 is again an infinite product. You've got a McMahon factor again, m minus y0, y1 squared, and then there is a product m greater or equal to 1, 1 plus y0 to the m, y1 to the m minus 1 to the m, 1 plus y0 to the m, y1 to the m plus 1 to the m. So that's the result. So as I say, this is a kind of theorem. I mean, there's two parts to the theorem. One is to understand the localization, and the other one is to do a kind of McMahon type, to prove a McMahon type result for some sort of configuration. So the rest is sort of combinatorics. And so if you compare these two, so you have the x and then you have the j tildes, and so the formula suggests a kind of obvious change of variables. So that y is y0, y1, and then t is y1, maybe with a sign, minus. So then the two formulae almost match, except that we have too many factors. So we have these extra factors. So in this paper, I made two wild speculations. One of them was wildly wrong, and the other one turned out to be correct. So one of the speculations in that paper was that these extra factors come around by wall crossing, and that's true. So let me explain that.
Yeah.
The wrong one was that I thought that the pyramids with a long edge correspond to higher rank. I mean, that's bullshit. They don't correspond.
You're on camera.
Right. So okay. So let me explain the wall crossing, or at least let me explain the walls. So this is kind of part 3, wall crossing. So this was a stunning paper of Nagao and Nakajima. Stunning for me. They answered this question very beautifully. So they understood really what was going on, and of course their starting point is again kind of classical. If you see, one stability condition, then you should think about all of them. So Alice said all this to us a long time ago. So we want to study reps of Q tilde or J tilde, really with relation, with still the dimension vector of v comma 1. So we don't change n comma 1. So we don't change that. So the rank is still the same, but change the stability condition. But with stability parameter some zeta, which is zeta 0, zeta 1 in R2. So in all these problems, when you think of quivers, there's really an R3 of stability parameters, but that one direction kind of is kind of can be factored out. So one either assumes that the sum of the weighted dimensions is 0 or something. So in any case, there's a kind of translation invariance which you can forget about, and the effective space of stability parameters is just this R2. And so then there is this wonderful theorem which describes completely the behavior of these moduli spaces and their interpretation at least at a dense set of points on R2. Well, and on the walls as well, but that's slightly more complicated. So, I mean, so there's nothing, I mean, there's some hard work going in there, but I mean, everything I say is kind of well known, that in this situation you expect walls, and the walls in a chamber, the moduli space doesn't change. When you cross the wall, it changes somewhat. The point about this example is that you can understand everything completely explicitly, and so you can make computations and so on. So, so here's the theorem. As I say, this is a result of Nakajima and Nagao. So R2, this parameter space, admits a chamber decomposition with countably many chambers. So this is what it looks like. So in some very, very natural parameters. So this is all one chamber, and this is also one chamber, and then maybe there is a kind of thick wall across there. So that's one of the walls, and then less brutal walls like this, where the slopes are sort of n over n minus 1, and also on the other side. So there's a half slope one, and then a next one is kind of like this. So the walls accumulate towards the nasty walls. So that's the decomposition. So there's a chamber indexed by some integers. So this is the first one, and then the second one, and so on. And then there's a first one, and so on. And similarly here. So there's the first one, a second one, and the first one, a second one, and they become dense at the yellow wall. And so so part of the theorem was to say, okay, so if you don't change within the same chamber, the moduli space of representations with the suprapotential and the dimension vector doesn't change. The set of walls are parametrized by a set delta, which can be, so there's some real positive roots, and then imaginary roots, and then real negative roots. So these are the guys I minus 1. There's just one. I mean, the way I think about it, there's just one root here. I mean, it depends on how you write the whole story, but let me just write this as here we really are writing the I plus 1. So here I is at least 1, and here I is at least 0. So these are the normals to each of the lines. So there's one wall for each of the set of roots. And moreover, and that's one of the most exciting parts of the paper, so in each chamber, or in some of the chambers, we recognize some moduli spaces that we knew. So some chambers give well-known moduli spaces. So what are they? So here the moduli space is just a point, meaning that the only stable representation is the one where the dimension vectors are 0, 0. There's no other stable representation. So this is where the original cyclic story happens. So this is cyclic modules. This is a chamber of cyclic modules, and then you sort of start crossing the walls, and the next statement you can make is about sort of close to the yellow wall. So meaning that depending on n1 and n2, you have to be sufficiently close at finite distance to get to, in this particular case, some dt moduli space for x. And on the other side, the pairs moduli space for x. So this is stable pairs, PT theory. And similarly, on that side, there is sort of dt moduli space for x plus, and for the flop, and here there is the pairs moduli space for x plus. Close to, I mean, there isn't a kind of bounded chamber there, but depending on your dimension vector, you have to be fairly close to the yellow line. So the point is now that you can now fully incorporate everything all the moduli spaces you wanted to know about, so non-commutative dt, the dt, the pairs, and also the flop, it's all incorporated in kind of one picture. And I really like this picture because somehow we've always known the wall crossing on the yellow line. So the yellow line represents the Picard group, right? So in the Picard group, we used to have the real Picard group, x on one side, then the flop, and then x plus on the other side. So that's kind of the classical picture. If you draw wall crossing from x to x plus, then there's just one wall. This is this old picture of, the Kähler cone, but also a picture of Witten, that you kind of reduce the Kähler class, then you do something, and you come out on the other side. So this picture, somehow, it's a real picture still. It's not the complexified Kähler cone. It's a real picture. It's R2, where you've kind of gained one more dimension when you think about the kind of full representations of this. So your old Picard group picture now gets included into this much more refined picture, where you got lots and lots of walls and a lot of stuff going on. But of course, it still makes sense to go from dt of x to dt of x plus, but you need to do a lot of stuff. And okay, so now you can write kind of more general generating series. So this is going to be the partition function of j hat modules with a particular stability condition. This is still a function of y0 and y1. And so there's a kind of I should call this a theorem. So this is Nakajima and Nagao, and this way of writing, somehow this was discussed in a physics paper of Chung and Jeffries, who realized, who sort of essentially had the same picture in a kind of described in a kind of physical way and a physical motivation. But they also noticed this nice way of writing the formula, which says that this generating series is now product over all alpha in delta, and then psi dot alpha positive, so that's just the inner product, just a normal 2 by 2 inner product, z alpha y0, y1, where you can say explicitly what these z alpha y0 and y1 is. So it's kind of 1 plus or minus y0 to the alpha 1, alpha 0, y1 to the alpha 1, the minus sign perhaps, and then either plus alpha 1, 0, or minus 2 alpha 0. So there are these two undetermined things. So you choose the pluses for real, and you choose the minus for imaginary. So this part will contribute to your McMahon factors. Alpha 0 is equal to alpha 1. Then you get your negative sign here and your McMahon part, and then the other contributions. And of course, that fully explains what happened when we went from here to there, because we've just done a bunch of wall crossing. So one series, the X series lives here, the J series, the J hat, the cyclic one lives here, and we've just done exactly a countable number of wall crossings, which gives all those extra terms. Okay, so that's kind of very pretty. Right, went quite fast. Any questions? Okay. So this is all still the old story. So let me talk a little bit about the refined vertex. So why this is still fairly old now. So the motivation to think, my motivation at least, to think about some sort of refined invariance at all was this quite, from my point of view, enigmatic paper of Iqbal, Kustches, and Waffa called the refined topological vertex. So what is the refined vertex? So remember we had these C's. They are now gone. And most general, so you've got three partitions, 3 lambda mu of Q, and I said it's some kind of combinatorial generating series. So sum Q to the alpha, where alpha is a 3D partition with some asymptotic. So alpha, sort of the limit in the 3 directions is lambda mu, meaning that you're supposed to think of a room corner and throw some stack of boxes, set of little boxes down there, which then have 3 infinite legs with certain profiles. So here there's some profile, and then here there's some profile, and then here there's some some profile. So this is lambda mu and nu. And these are infinite, so this weight of alpha means a kind of renormalized volume where you take away some uniform expression. Okay, so as I said, this is a kind of complicated combinatorial sum, and this was studied by lots of people, but Okunkov and Reshetikin maybe for the first time in maths. And in particular, then there is, let's see, empty, empty, empty Q, which is, so I don't allow any infinities, so this is just the sum of all finite 3D partitions. And that's a classical result that this has a nice product formula. This is just called the McMahon function. It doesn't really matter what the product formula is from this for this talk. Now, what these guys do, so this is Iqbal, Kostjazin, and Vafa, they refine all of these expressions into two-variable series in the first instance, anyway. And they do it in a rather strange way. And the way they do it, at least from a math point of view, is still unexplained. So I'm going to eventually come up with some theorems, but explain some theorems, but the relation to these expressions is still very much unexplained. So what did they do? So let me just do this one. So they say C empty, empty, empty. Now I've got two variables, u and v, and they do this kind of very strange thing. They say sum alpha 3D partition, and then u to the alpha plus, v to the alpha minus. So what are you supposed to read here? So alpha now lives once again in sort of three-dimensional space. There's some little boxes here stacked together. And now you're supposed to choose a direction. So you now fix an axis. Okay, so that's fine. We've broken the symmetry. And now we just brutally cut this partition through with a plane. So this plane now has some equation x minus y equals. Okay, so x minus y equals what? So x minus y equals, say, delta. So there's some parameter here, again, which has just been a discussion of some lunchtime conversations, but it's not totally explained. But anyway, let's take, so the one I've drawn is delta equals 0, but you can move this plane wherever you want. And then the alpha plus and the alpha minus are just counting the number of boxes that happen to lie on the right side of the cut or the left side. And if your cut actually cuts through some boxes like this one, then you count half and half. So it's some kind of strange combinatorial game, and it's completely unmotivated. So this is nice and symmetric, and we fully understand this. This is just torus localization. Yes, you have to put in the weights, and there are some miracles that happen, but this has a full mathematical understanding, whereas this one doesn't. I mean, it's this particular one still admits, for example, an infinite product expression, which again isn't really important for us, but okay, so it's some kind of combinatorics whose role is not completely clear. And if you want to do this more generally, so if you want to do the general one, then you just do some kind of goddamn complicated thing. Some kind of sum, and then you have to put in some kind of weight. It's the same sort of thing that you did before. Oh, it's gone. So you're taking the sum over all, yes, here. So you take the sum over the same kind of configurations, but you have to somehow put in some, again, some plus depending on lambda mu nu, and some minus depending on lambda mu nu. And the combinatorial rules are quite baroque from our point of view, and I don't really understand them. But anyway, there's some kind of well-defined expression which generalizes the topological vertex, and so this is called the refined vertex. And in particular, so remember we used the empty lambda guys to compute the partition function of the conifold, and that computation still works. So you can compute this R is going to be my refined, for lack of better temporary notation. This is the refined partition function of the conifold geometry. So this is the large volume thing, T. And it turns out that it just makes sense to do the same kind of thing as you did before. So you sum over all partitions, C empty lambda, UV, C empty lambda transpose UV, and then T to the lambda. And so you get an answer which has one part which is uncontroversial and another part which is slightly controversial.
Does it depend which ways you choose the planes and the
Yeah, so the combinatorics is quite arcane and important, and I can't give full justice to it at all, partly for lack of knowledge. So, I mean, what I told you for empty, empty, empty is correct. So you just slice it in this diagonal fashion. I mean, remember the diagonal is not so unnatural from the point of view of Andre's proof of the McMahon function. I mean, that's the same kind of slicing as the one that gives you the operator identity. So that thing, okay, I mean, they break the symmetry. So it's the same kind of symmetry breaking. You choose a direction, and then you slice like this. Actually, it turns out that you can slice completely. So there's an infinite variable generating function which generalizes McMahon, which is still an infinite product, where you give each slice a different weight. And that's got some representation theoretic significance. But anyway, so what I said for C empty, empty, empty is completely precise. And then the question is just how do you distribute, I mean, what's your delta? And I'll comment on that a little later. So now, what happens for arbitrary lambda mu nu? I asked Tudor, I don't know. Something complicated. You have to push things around, and I mean, I don't understand it.
I think he's pointing out that when you're doing this gluing of two of them, you're choosing sort of a direction for each of the two vertices
right.
you glue together, and you're making some specific choice.
Yeah,
there.
right. I mean, I guess that's implicit in this. Yeah. Okay, so so the answer is still there. Very good. So there's some sort of similar thing happening there. So let me just delete this. So I said that the formula. So here I'm continuing that. So this is the refined one. So the refined Z X is, so as I said, it's got an uncontroversial part, which is product ij greater or equal to 1, and then 1 minus u to the I minus a half, v to the j minus a half, inverse. No inverse, sorry, and the t. Okay, so that's uncontroversial. Maybe I should say that would probably help. So the specialization is just u equals v equals y. Okay, that's your specialization, and that gives. I mean, that should be obvious. I mean, if I just make these two the same, then I haven't done anything. So I'm going to get back my original topological vertex, and that should be the specialization in these variables that you're supposed to take.
When you glue two of them, the planes have to be parallel.
Yeah, right. No, sure.
Maybe
Yeah.
that's
Right. Okay. Yeah, they have to be. Yes,
and it doesn't matter which way they're aligned as long as they're parallel.
Thank you. Right. So okay. So this part you can compute very explicitly, and then there is a kind of question, and you see this is just a precise generalization of this now specializes to this. I mean, maybe I lost the sign. No, I haven't. So maybe u equals v equals minus y. I mean, it's a question of where I stick the sign. I mean, there is actually a correct treatment of signs here, but let me just kind of ignore that. So this part specializes actually to that part. So that's the refined. This is the pairs part. This is the part that's contributed by the curves together with the sections. And then there is the McMahon factor, and there's actually some question about how do you refine that, and that depends on that value of delta. So I mean, in the original paper, or maybe in a paper of so there's Dimov Tegukov, so Tudor with a paper with Sergei, they've chosen a kind of symmetric refinement which corresponds to delta equals 0 square. But as it turns out, that's not actually, at least from the math point of view, that's not the right way to go about it. But so there's some kind of question mark as to what that becomes. That depends on what deltas you choose, but the rest is somehow uncontroversial. So that should be, so that kind of function is the function we're looking for. So that's the refined dt series of the conifold. So then, sometime around 2 or 3 years ago, various people realized, partly inspired by Soldam and partly by DG, and I guess ourselves, we thought about on similar lines, that an interpretation of this should come from, so this should really be some kind of motivic or categorified invariant of, maybe I need this picture actually, okay, let me leave that on. Some kind of categorified or refined invariant of the conifold, or more generally, of course, arbitrary C by 3 categories or spaces or whatever. So let me talk about motivic invariants. So with the 2 talks beforehand, I should have everything in place so I can just kind of crack along. So so what's important here is, so there are these moduli spaces of Nakajima and Nagao. So Nakajima and Nagao give us generally, these moduli spaces, where you take these dimension vectors, talk about j hat, that's supposed to be a I, and 0 and 1. And they sit inside some kind of moduli space, still at stability. Now, moduli space is for the unbound quiver, so no relations. And these guys are very nice and non-singular. And that's sort of standard in this subject, so these are smooth. And then there is a function here, which is trace of w, which is just a complex valued function. So as explained by Kantaro, these guys are singular, they sit in these nice smooth spaces. And really the correct way to think about that is that it sits in the stack of all q hat modules, q tilde modules. And really the function is a global one. So that's very important. So this is why for us, this question that Kantaro discussed at the end doesn't actually arise. All these guys sit in the same stack and the same function. So there's no problem with I mean, as long as you can compare something, you know that it's the same vanishing cycle somehow. So all you really need to understand is what is the change when you go through one of these walls. But there's no issue of comparing the superpotentials because they all come from the same stack. So that's good, and then you can sort of define these. I mean, my job was to sort out the notation. I failed badly, so I'm just going to call these Motivic DT invariants. I mean, there's too many labels: phi, j hat, and 0 and 1. So they live, and again, I don't have to say where they live. So they live in this ring that has already been introduced. So this is the K0 of the varieties. You invert something, and in particular, I do want an L to the half here. So that's important. So we're taking the version that Kantaro already had, where you are formally adjoining square root of the left-chest motive. And so the definition of this has already been given by Kantaro. So this is the minus L to the minus half the dimension of the smooth guy times the Motivic vanishing cycle of trace W. So remember here we have the stability condition, so there is no stackiness on this side of the picture. This is all just a variety, and this is all very, very nice.
You're always working with Q tilde and J tilde.
Yeah. I am now, yes. Those are the ones that are nice and non-singular, right? That's why you don't get stacks, because you...
Is the tilde means framed?
Tilde means framed, yeah. So these are always framed. Yeah, framed rank 1. I'll get to the unframed in a minute, but... Right, so I mean, let me just write down our theorem, and our theorem is precise. It's kind of the intersection or the common push out of that formula. So remember, that formula was the numerical DT invariance at arbitrary stability condition expressed in terms of these pretty expressions involving the roots, whereas the formula I may have just deleted was no, it's up there. It's the refined formula, but that we believe is just at the particular stability condition, namely a large volume, so somewhere around here. So if you kind of put this together, it's very clear what the if we've known for at least 2 years what the answer has to be. It's taken us some time to prove it, but I believe now it's a theorem, and in fact we have at least 2 or possibly 3 proofs now. Sure. So this is, I mean, I'm going to put these names here, and then there's a kind of separate proof by Ben. So I guess I should say the contribution of Ben Davison has been to think really hard about the orientation data. So I'm avoiding that. So we are avoiding all mention of orientation data by taking these reasonably canonical embeddings into smooth spaces. So then we never have to worry about orientation data because all the motives come to us sort of consistently. If you don't have that, if you only want to think about the moduli interpretation of this, and you think real hard, then SKS discovered you need some extra data. You need to correct for some non-uniqueness in some quadratic form that turns up in the infinity structure. And if you think about that very carefully, you get this question of orientation data. So at least for this particular case, but much more generally, Ben's thesis sort of thinks real hard about that and proves some conjectures of KS and just gives a slightly more digestible account of what's going on than perhaps the original. So anyway, what's the theorem? So the theorem says so that this motivic generating series. So I haven't defined that. So you've got this motivic dt invariant. So then you have a motivic generating function, j tilde, some dual variables y0 and y1. So where does this live? So this now lives in this ring with, formal power series with coefficients in this ring in y0 and y1. Okay, so mz at xi, j tilde, y0, y1 is again a product. It's exactly the same story. So it's a product alpha over delta, alpha and delta, xi dot alpha is positive, z alpha, y0, y1, these are motivic z's. Okay, so as I said, this equation happens in that motivic ring with all these decorations, and then y0, y1. So you still get this full decomposition, and you can say what the factors are. So for alpha real, the factor is, okay, so before we had just a single term raised to some power. So now we have a refinement of that. So this motivic z alpha y0, y1 is a product from j goes from 0 to alpha 0 minus 1, 1 plus, okay, some power of the left chest motive, alpha 0 minus a half minus j, and then y0 to the alpha 0, y1 to the alpha 1. Okay, so that's what it is for real roots. And then there is this question as to what's the imaginary root. So that, remember, corresponds to our yellow line, the kind of the dt-pt wall, this kind of hard stuff where the Hilbert scheme happens. And so so for alpha equals 1, 1, whatever it is. So remember, before it was a square. It was just a square of the McMahon function. Now it's not a square. So it's this refinement of McMahon at delta equals minus 3 halves. Okay, let me put y0, y1 here, and then m at delta equals minus a half y0, y1. Okay, so there's some expression, and there is a change of variables, and the change of variables is a fairly obvious one. So remember, we have to change some variables because in the physicist notation, we had the specialization was u equals v. The specialization here, the deformed variable here is this L or Q, which you want to set to L to the half to be minus 1. So there's some change of variables that happens. But up to that change of variables, these terms are exactly matching the terms, the contributions in the part of the refined function, which I said was uncontroversial. And then this is the precise, at least from our point of view, this is the precise refinement that you need to take. And this is something we knew already from this earlier paper with Kai and Jim, because what these deltas really refer to in our formulation are representing the cohomology of your original space, so cohomology of X. So the 3 and the 1, everything is shifted a little bit, but they shifted down, but they refer to the degree 0 and the degree 2 class that exists on local P1. So for example, if I only did C3, then the result would be just this, representing the fact that C3 has only degree 0 homology. And we have a very general result just for the Hilbert scheme, which says that you get these factors, but every factor you get to the raised to the power, which is the corresponding Betti number. So that's kind of the explanation here. Right, so let me just say, so that's our main result. Let me just say a few words about what goes into the proof. So again, most of the methods have already been mentioned today. So so the proof. So the first thing to do is basically Nakajima and Nagao tell us what happens at least at most of the walls. Well, in some sense, they tell us what happens at all the walls, but certainly they tell us what happens at most of the walls. And what happens at most of the walls is there's just kind of one representation and its powers, like in Kentaro's talk in a different context. And so you have to kind of understand the contribution of that part. And the first step you do is you do some kind of whole algebra identity. So, so you sort of think about stability, and then you go to some whole algebra identities. So as is now standard in the subject, you want to move from there to identities in the quantum torus. So the connection here is, of course, the integration map. So here is the KS integration map. But I mean, in this Motivic formulation, as we understand it, the proof that that integration map is actually a map of algebras partly involves all this hard stuff with the orientation data, and it still depends on this integral identity. So you can kind of replace that, as Kentaro already hinted at, you can replace that by the torus section. So if you replace the proofs or their arguments with an argument that explicitly involves the torus section, then you can actually prove quite simply the fact that, that this map is actually an algebra homomorphism. So actually there are, I mean, Kentaro thought about this real hard, and also Sergei Moscovoi. So there are now accounts in the literature which say that, I mean, you do the KS map, but to actually prove that it's kind of well-defined to our full satisfaction and it's a map of rings, you include the torus section. But with the torus section, it works very well. Okay, so now it's very important what kind of quantum torus we talk about. So there are two quantum tori here. There's the one corresponding to J, and then the one corresponding to J tilde. So I think Kentaro again introduced, so maybe even Jim also, or Jan, we've seen the quantum torus. So the quantum torus is a non-commutative algebra which has kind of variables corresponding to all weight vectors, but the relation involves the inner product. Now the point about the inner product is if I delete that vertex, then this is a completely symmetric quiver. If you remember what the inner product is, it has something to do with incoming arrows minus outgoing arrows. So that's actually identically zero here. So this is a fully commutative torus, whereas this is kind of mildly non-commutative. There's a little bit of non-commutativity here, which is very good because it's not fully trivial, but there's not too much. There's just this one part which is slightly non-symmetric. So you can play off these identities against each other, a bit like Naga was explaining. And what you get is I mean, there are various ways of writing it. You can either get this full expression out of some universal expression, or you can understand wall crossing one by one. So we have two slightly different proofs now. But anyway, you can completely understand everything if, and that's important, you need a starting point. So you need one extra computation. So you can sort of choose whichever you do, but you need to do something. So in our treatment originally with in this Darren Bryan paper, we sort of computed the cyclic one in terms of something which turns out to be dimensional reduction. So you can essentially do that as the way Jim explained in his talk this morning. I want to put a slightly different interpretation to a computation that I've seen. It's really not, I don't have anything to do with it, so I think it's very nice, and it's due to Sergei Moscovoi. So how to compute what? So how to compute something non-trivial, because so the trivial wall crossings take you from nothing to maybe this part of the diagram. You need to understand what happens when you cross here. And then again, you understand what happens on this side. Or if you do it in one go, then you have to have some seed computation. And so, in some sense, the elegant one to compute is the so-called universal series. So now we are back to J. We throw out this stability condition. And so we go to this Stacky series, which Kentaro already talked about. So this is the generating series of stacks rep J with various vectors. So this is some kind of universal series. And okay, so Jim gave us some story of how to compute that, but let me give a slightly different story. So so I at least for for now, I call it sort of double-dimensional reduction, which seems to work very nicely in some situations. So this assumes really very special properties about. So let me say that here we're doing some very explicit computation, like this one. And in general, you don't expect to get a fully explicit answer, of course. So there's something very, very special going on in a certain class of quivers, which might include a few more than are approachable with other methods. So I mean, of course, you use the torus section to make one reduction. So this was already explained by Jim and Kentaro. So you kind of essentially reduced a 2D situation. So it was very apparent why. I mean, we discussed this at the end of last talk. Why is this a 2D situation? So for example, from C3, you kind of explicitly reduce to C2. What happens in this conifold example is, on that level, slightly less transparent, because you go from this Q to what Jim should have called Q bar, maybe the reduced quiver, where you take out a cut. So here there's only, so there are 2 and 1 here. Okay, so that's the first step. But you can actually fiber that now, so representations of this, you can fiber it over, so I should say this is very much a trick that I learned from Sergei Mozgovoi. You now fiber that over representations. You do one more reduction. You knock out another arrow. And now you just have this. Now, okay, so you have to do this systematically. You have to understand the fibers, but that's not too bad because the way the relations look, this is a linear problem. So every fiber of this is a linear space. You're solving some equations where the matrix appears, the matrix you lose appears in a linear fashion. So okay, you of course have to control the dimension of the fiber, but you know, these fibers are not too bad. They are just defined spaces. And then what's the base? Well, the base is just a Kronecker quiver. So you have a full classification of representations of the Kronecker quiver. So what do you need to understand? You need to kind of enumerate these, write down a list, understand the fibers, and stick it all together. And it works, and it gives a formula that was obtained previously by Andrew Morrison using the method that Jim explained. So this method, so this is a kind of one-dimensional problem. I mean, why is it one-dimensional? For example, it's P1 in more than one way. It is representations of this are sheaves on P1, but also the moduli space. It's a tame quiver, so all moduli spaces of representations of this are at most one-dimensional. So that this is somehow very strongly a one-dimensional problem, and it's completely under control. So you can, with some work, and the work is going to include the same kind of power structure tricks that Jim explained to us, but it's a slightly different method of getting the same formula. So, okay, so that's...
But I was going to stop you for a second. The whole of the rest of the talk was about the one with an extra arrow.
Yeah, right. Okay, so I didn't explain how you went from there to there. So that's a question of how you go from frame to unframe. That's sort of essentially in our paper. There's some technology to do that. Sergei has a paper which will explain this in kind of full generality. But so yeah, so that's actually not too hard. That's to go from frame to unframe. There is some kind of universal game that you need to play. Yeah, that's right. It's non-trivial, but it's under control. So here, yeah, that's right. So here we've forgotten about the extra arrow. And now we are doing this two-step dimensional reduction. Okay, so that's kind of in a nutshell the end of the proof. So if you put all these steps together, then you get our formula. And really the only reason why I think it was worth writing it out is that in particular, this is the first time that you get a fully categorified or fully motivated version of an actual DT series, something actually involving curves. So this is actually the first example. Of course, it's cheating because we haven't really seen the curves anywhere. The curves come in through a kind of very roundabout route. But anyway, this is a computation of an actual full motivated DT story and not just some quivery stuff. So I think it's interesting from that point of view. So there are other cases that this should work for. So essentially, anytime you think that DT should have a fully explicit infinite product, probably the refined DT will also have one. So there's some work in progress with various members of the team, certainly excluding me. So you could think of slightly more general geometries like the SPP, the suspended pinch point. More interestingly, you could do, so Jim mentioned that, but you could do C2 mod gamma times C, but maybe without the assumption of, assumption of abelian abelian gamma. So Amin Gonanpour and Yifan Zhang have a paper on just the unmotivated DT, but the motivated computation should work in the same way, assuming that one can do this. And I think there's hope that this method actually works, because what you get in this case, after 2 reductions, so Jim again said the first reduction, but after 2 reductions, you just get the affine AD quiver. So again, that's tame, representations are understood, so you should be able to work out what happens. So this is again work of Sergey, and I mean the one that Jim didn't mention, but it's sort of lurking in the background, is C3 divided by Z2 cross Z2, which, okay, so that's harder, but these are the cases where you probably expect full product formulae. There are of course generalizations of this to these kind of strip geometries studied by Kentaro. So so just to summarize, I think now there's a kind of pretty good framework where we understand some of these computations when they work. Perhaps just one final thing to say is that we have used a lot the torus section. So the full KS story doesn't need a torus section, but the bits that we can sort of prove completely use the torus section very heavily, and certainly more or less explicitly the torus section plays a major role in this dimensional reduction story. But what's completely not understood is localization. So there's absolutely no reason, at least I don't know any real reason, why you shouldn't be able to compute mathematically these contributions just from these toric pictures. But it seems quite hard. So that's still a big outstanding question. Okay, thanks very much.
Questions?
The main example on these ones you list at the end are all toric threefolds without compact exceptional divisors over the singularity.
I mean, the D and E are not toric, but not too far off, yeah.
Bad divisors.
Right. So
these
compact
have to be
exceptional
non-compact?
4 cycles, I suppose, I mean, that's very hard. That's always very hard, much harder. I mean, in particular, even the normal DT series doesn't have in most cases at least, doesn't have a fully factorized form. And also wall crossing is much harder. So
I mean,
Can
the
I-
resolutions of those guys are kind of on the same footing, right?
Sorry?
You were asking about the resolutions of these guys.
I mean,
yeah, there's no compact 4 cycles in any of that. That's true. And I don't know. Yeah, so those are harder. So in particular, the wall structure. So in all these cases, you expect discrete walls. So this particular one would be just the chamber structure of the affine Lie algebra. So once again, you see something like the Kähler cone in the slice for the finite dimensional Lie algebra, which is a finite decomposition into Y chambers. Then on top of that is the sort of countably infinite one, but it's still nice and discrete, and things should or will be under control. And the same for all these cases. As soon as you have something like a P2, everything is much harder. So the stability conditions are much harder. Physics is much harder. Everything is much harder. And I don't know any. I mean, you can use a topological vertex to work out the DT theory, of course. That's a theorem. And then in some cases there are predictions for refined DT. So up until an hour ago, I was under the understanding that, for example, the topological vertex, the refined vertex, cannot even be constructed for local P2. Now, Tudor tells me that there is a trick to do it. But there are framing issues which are actually more subtle, as in Vivek's question. The framing issues are more subtle for the refined vertex. And obviously, at least if I look at it from just a triangle, it's kind of quite hard to arrange these walls in a consistent fashion. So there is some trick that you can do. P1 cross P1 is fine. That's a square. So I can put these planes in kind of parallel. And you get a conjecture for the refined DT series, but it's not an infinite product. It's some big complicated expression, and I don't know any theorem. It's defined, at least at the non-commutative point. You have a definition from the quiver, maybe not at the DT side. Certainly, probably not at the DT side at the moment. But you get some conjecture as to what it should be. But I don't know. It's not a theorem.
Is there any geometric counterpart to this dimension reduction, like pushing sheaves down to the P1 or something?
Yes. I mean, something like that's going on. I don't know a precise statement. I mean, this is all pretty new, and maybe Sergey is angry with me that I actually told you. Right? But anyway, I mean, it's just a story now. I mean, you can actually construct a proof. I mean, let me just say, if you do C3, you get a slightly different proof for the commuting variety. I mean, there's one-dimensional reduction, and there's the second one. You just get C. This is not geometric, but it works. I mean, you get the quiver for C. The representations are, in this case, just Georgian blocks. And you can reconstruct the commuting variety proof, which is probably essentially the same proof as Jim's, but possibly slightly differently phrased. But here it's not, I don't know, but it would be nice, of course.
Double dimension reduction just means you've got a 2 torus instead of a 1 torus. Or you really have to...
Well, it kind of is. You kind of knock out another eigenspace of the torus, but I wouldn't want to push it. I mean, I just think, the things you get in the end are one-dimensional in some kind of genuine sense, but and it's probably, in the second, you don't explicitly need any torus section anymore. You literally just fiber reps of this over reps of that, and you count. The explicitly you don't see the torus. Now, implicitly, maybe it's still there, and the reason why it works is that. And I should say that this really works in a very small number of cases, right? This isn't a general scheme to do anything general. It works in a few cases, and it works very nicely in those cases. Certainly, lots more things have a large torus section than the things for this this works, right? So I don't know, not explicitly.
I'd like to ask just a quick question. So maybe you're hinting at something, or you wrote these as roots, as if they were the root system of some affine Lie algebra. What is the affine Lie algebra, and what's its story here?
This is okay. Maybe I should have said that. This is the other $1 million question in the subject, right? Why on earth do we see? Anytime you do this kind of stuff. For this, we understand. On this side, of course, Nakajima's results on how the affine Lie algebra comes in, but this is a slightly different story, and why in this case you see the roots of SL2 hat very explicitly, I don't know. There are results in physics which suggest many more analogies of this nature. So, for example, there's some work a slightly different work, but possibly related by Lotte Hollands and Miranda Chang and other people who see similar patterns, much bigger algebras, affine cosmutes acting on things to do with invertive invariance. Slightly different story, black hole counting or whatever, I don't know. And in all these cases, it's a begging question as to what on earth is this algebra actually acting on. You see the root system, you see weight spaces appearing, you see a large part of the representation theory appearing, and there's no full explanation as to why it's all that.
These are the dimension vectors of the indecomposable representations of the conical group.
Yes, yeah. Well, yes, but
what more do you want? That's combinatoric.
Yeah, right. I'd like geometry. I'd like to say that write down some. Like the work of Nakajima Grojnowski. Write down some set of spaces. They have cohomologies, or now we have a guess, and implicitly we of course have that now. The Koha. Koha does exactly that. Koha gives you a set of algebras. So, maybe you will see once you understand the Koha for the conifold, you'll see some affine SL2. Jan, do you believe that?
Yeah.
Okay, good. Right, so he believes that. Okay.
Are there any further questions? All right, well, let's thank Balazs again. Thank you.